within walking distance who are watching on YouTube, come on over, join us. On light sources is by Amedeo. This is over at SLAC, the one that Craig mentioned, the free electron lasers, which are a slightly different setup than the synchrotron and pose slightly different problems. So, Amedeo, please take it away.
Thank you. So, I divided my presentation in 4 parts. I will introduce the LINAC coherent light source in the beginning to give you an idea of what a free electron laser is trying to do. Then I will talk about how we plan to build the data system from an infrastructure and software point of view. I will give some example of what it means to do on-the-fly data reduction for free electron lasers. And then I will talk about this quasi-real-time ability to do data analysis using a supercomputer, which is something that Craig already introduced in the last talk, but from the free electron laser perspective. So the LCLS is hosted at SLAC. We took over the linear accelerator that in the past was used for high-energy physics experiments like Babar. In particular, LCLS-1 took the last third, about 1 kilometer of the accelerator, to generate electron in the 2.5, 15 JeV range, and then sending these electrons through an undulator that wiggles the electrons, generates photons that then interacting with the electron themselves generate a resonance that creates these very short pulses, few femtosecond pulses, of very intense, of the order of 10 to the 12 photons, that then we distribute to the near experimental hall and to the far experimental hall, where we have right now about 7 experiments, 7 instruments rather, where we try to use this 200 MeV to 12 keV X-ray to do different kind of science. This is how the near experimental hall and the far experimental hall look right now. We have 7 instruments that do fundamentally very different things: atomic molecular optical science, soft X-ray, X-ray pump probe, coherent X-ray imaging, and matter in extreme condition. And we have already had a significant impact on many areas of science, from resolving structure of protein complexes that were not accessible before free electron laser capabilities, capturing bond formation in transition state of chemical reactions, probing extreme states of matter, where we have petawatts laser that we use to excite the sample before the X-ray come down the beamline to take a snapshot of these samples. One way to look at LCLS is like one big microscope. But the main difference from a microscope is that you don't have a lens that takes care of generating a nice image that then you can look at to get an idea of what the sample looks like. Typically, these experiments will generate diffraction images that are not that useful to humans to understand how the sample is actually looking. So one way to look at LCLS is that instead of having one big lens, we have computing capabilities that through data processing and scientific interpretation, which both demand intensive computational analysis, can give you some insight about the kind of interaction, the kind of sample that was on the beamline. As I mentioned, these X-rays are extremely fast, they're extremely short. So you can think of them as like flashes from a strobe light that produce stop-action movies of atoms and molecules. Keep in mind that if you remember the accelerator that I showed in the beginning, I said that we are using roughly a third of the original LINAC at SLAC. We are going through an upgrade in 2020 called LCLS-2, where we will install a superconducting accelerator in the first part of the LINAC that will increase the data throughput by 3 order of magnitudes by 2025. And the pulse will actually go from the 120 hertz that we have today to 1 megahertz by 2021. And then later on, we will use the entire LINAC, and for a second upgrade that we call SLS2 high energy, where we will still operate in this, hundreds of kilohertz, megahertz regime, but we will operate with higher energy photons.
Amedeo, could you comment on how long an individual experiment typically runs for and what the data collection looks like? And
Yes, I actually have a slide that we call a day in the life.
Okay.
Regarding the experiments, well, I don't say anything later, so let me say now. Typically, we run between 150 to 200 experiments per year. We run for about each experiment for 5 days, either day or night, alternating 2 experiments, one during the day and 1 experiment during the night. The amount of data that is collected during these 5 days changes dramatically from experiment to experiment. It can go from a few terabytes to about 250 terabytes per experiment. Of course, these are the SLS1 numbers. For SLS2, we have a factor of 1,000 more data than we are expecting. Let me show you a brief movie here that shows how single particle imaging looks like. This is the sample that is injected along the beamline. This is the X-ray that is illuminating the sample. And this is what we get. This is a combination of diffraction patterns. And then eventually the final goal for single particle imaging, at least, is to reconstruct the electron density, the 3D electron density of a sample at the time that it was illuminated.
Question? Is this valuable for reaction kinetics?
Yes, it can be. I am not an expert. I'm not a biologist. My expertise is in building the computing system for us to be able to do this kind of science. But yes, that's one of the kind of science that we do in SLS.
A trigger for the reaction that has to be synchronized with?
Yes. We run what we call palm probe experiments, where there is an optical laser that is used to excite the sample. That can be anything before the X-ray comes into the picture, and then you can take pictures of a sample at different time of the excitation and the relaxation process.
So they turn it off during the middle to watch it after they excited up, then they...
Yes.
Okay.
Yes, because then there can be a delta with some jitter between the optical laser and the X-ray beam, and then you use this jitter to scan the relaxation time.
Well, maybe a nitpick, but the relative velocities of the sample that was coming into target range and the speed of light, are those comparable, or was that?
No. I'm talking about the time between the optical laser.
Just in your illustration here.
Yes. No, this is
the little green cloud.
This is a gas injector.
Moving much slower.
Yes.
Okay.
Much slower. Order of magnitude. Yes. The injection itself is an art form. It was one of the main challenges for SLS1. You don't want to have ice, which otherwise would illuminate the detector and break it. You want to have the right percentage of heat where you illuminate the sample roughly at 10% level. If you illuminate too much, then you end up having a chance of piling up multiple diffraction patterns in the same trigger. You don't want to have too few of them, because then otherwise you are wasting beam time. So this is one. The next 4 slides are about 4 different experimental techniques that we plan on doing for LCLS2. This is one of the first things that we will do, where instead of running imaging detectors, we will have digitizers connected to a kind of time-of-flight detectors, which gives you the ability to determine the position of this electron-ion that are generated when you first pump the sample with an optical lasers, and then later on you illuminate this excited sample with the X-ray. Then you generate these waveforms, which are relatively easy to reduce, to extract the time of flight and the position, and then you sum all of these events into intensity map from multiple pulses. This is, for us, is a relatively, from a computational point of view, relatively easy experiment, because both the computation that is needed is relatively low, and also the throughput, even if it challenges for compared to today's number, around 200 gigabyte per second input to the data reduction system, and then 5 gigabyte out of it. This is, it's kind of how we will start testing SLS2.
So 50% of the data is of no value?
For this kind of experiment, it's a factor of 50, right? At least. Okay. We could get even more, because fundamentally you go from a waveform to a time of flight, right? So you go from a digitizer waveform to a few numbers. So this is one example where we have a good reduction capabilities. With XPCS, or photocorrelation spectroscopy, things get more interesting when we start talking about few teraflop, tens of teraflop, and hundreds of teraflop for a computational point of view. Here the idea is fundamentally you create intensity map from multiple pulses by looking at the autocorrelation. This is one of the few experiments in SLS where you look at the correlation between different events. So you look at how the speckles evolve over time as a function of Q, as a function of a momentum transfer. And there are different kinds of science that can be done with XPCS. Again, for us, the main challenge of XPCS is that you need to consider events one after the other. For other experiments like nanocrystallography or single particle imaging, every event is fundamentally independent. This is one of the few cases where you have to look at events over time. Then the third science case that I was going to show you is what we call serial femtosecond crystallography or nanocrystallography, where individual nanocrystal are injected in the LCLS pulses. This is similar to the movie that I showed in the beginning. Then diffraction patterns are collected on a pulse-by-pulse basis. In this case, the data reduction is not done by trying to reduce the content of information within one image, but by removing the events where there was no hit, where fundamentally the X-ray missed the sample that was being injected. I will get more later about why this is a better data reduction for nanocrystallography than try to do Fisher extraction on the image, for example. The data analysis for nanocrystallography starts being computing intensive, right? For SLS2, we expect to range from 4 petaflop in 2024, when we start operating the HE upgrade, to 20 petaflop in 2027, when we will operate 60 megapixel detectors at 40 kilohertz. We first determine the Bragg peaks, then you try to determine what was the orientation of the sample at the time of illumination, which is called indexing. Then you create this intensity map from hundreds of thousands of pulses, and then from there you can reconstruct them through an inverse Fourier transform, the 3D electron density of a sample. But really, the big guns, computationally speaking, for LCLS2 will come with single particle imaging. In this case, you don't have a nanocrystal, you have one sample. It could be a protein, could be a virus. And so you don't have the Bragg peaks anymore. You don't have this ability to do crystallography anymore. And in this case, you need to go through very complex algorithms, typically iterative algorithms, that they try to use constraints as much as you can about a priori knowledge of a sample to then derive the 3D electron density. And this iterative nature of these algorithms will bring us to the exascale regime for single particle imaging. So, as I said, this is from the user perspective, how does data analytics looks like at the LCLS? First of all, we must be able to get real time, within 1 second, feedback about the quality of data taking. Are all the detectors contributing to each event? Is the hit rate of injector being hit by the X-ray high enough? Is what we expect? Is this 10% that I was mentioning? Or is it too high or too low? And then within 1 minute time scale, we must be able to get feedback about the quality of the acquired data itself. So here is really, is the data acquisition system, is the experiment fundamentally working? And here is the quality of the data good enough? Are we collecting enough statistics? Is the signal-to-noise ratio as what we expected? Is the resolution of reconstructed electron density what we expected? Then during off-shift, as I said, one typical experiment operates either at day or night. And during the 12 hours that are not taking data, that's when most of the computing happens. They need to be able to run multiple passes, typically of the order of 20 passes over the full data, to optimize things like analysis parameter and possibly change the code in preparation for the next shift. This real-time aspect of SLS is one of the key challenges from the computing point of view. Then later on, typically of the order of 4 months, the users keep analyzing the data, and they must have fast access to the storage for a period of a few weeks. Typically, right now, the retention policy is 4 months. And then after 4 months, we move the data to tape, and the users must be able to restore the archived data, to test new ideas, to test new code, to try new parameters. Yes?
Going back to sample injection of single particles, orientation is an issue. Can orientation be controlled in some sense?
No, it is not.
It is not. Dipole on it or something?
Yes, no. That's not, there is no magnetic field, there is nothing that will try to orient. But there are ways to then determine what the orientation was. And I have a slide about this technique.
So, how much data do you store? And where do you store it? You were talking about incredible data rates.
Yes.
Are you storing that, or are you storing some reduced?
No.
Yeah.
No.
Okay.
No. I'm getting to it.
Okay.
Yes.
Okay.
I'm getting to it. So, as I said, fast feedback is essential, both on the order of seconds and minute time scale, to do different kind of analysis. Another characteristic is that we have short, bursty jobs, which need very short startup time. Fundamentally, by the time that we submit the job, we would like not to be longer than a few seconds, so that then by the time they run, which is the data acquisition time, is completed, we can already look at the results. Throughput between the storage and the process is critical, and also the speed and flexibility of the development cycle is critical. There are many experiments with a very rapid turnaround, and we need to modify the data analysis during experiments. These characteristics are fundamentally different from typical usage of a supercomputer to do a simulation, for example. So these are an example of peak throughput. This is for the throughput that we expect starting from today to the advent of LCLS2HE. We are talking about terabyte per second. So we fundamentally need to do something way more drastic than we did in LCLS1, where we were storing all the data. We will need to do data reduction on the fly for LCLS2. The other challenge for us is that we are developing algorithms, like the one for single particle imaging, that will require exascale capabilities. how do we decide that this was exascale? The idea here is that if you impose the requirement that you want to keep up with data taking rate, then you need to be able to fully utilize the capability of the machine in order to have enough cores that allow you to keep up with the throughput from the beamlines. So this is how we plan to build the LCLS2 data system. So as I mentioned, the detectors by 2026 will generate of the order of 1 terabyte per second. For LCLS2, we will do something that we haven't done for LCLS1, which is to reduce the data in such a way that we keep only the science content that is needed to do the analysis. So everything that is not strictly required for science is thrown away at this level. Also connected to the data reduction pipeline, we will have an online monitoring system that will provide this 1 second fast feedback analysis capability so that the user can see what's going on at any given time. Otherwise, they will say, it's like flying blind in the beamlines if you don't see what is going on at any point. The idea is that this data reduction pipeline will provide at least a factor of 10. Right now, if we look at the experimental techniques that we expect, this is actually very conservative. Many experiments will be of 2 orders of magnitude data reduction. We will go send the data to a fast feedback storage system where we provide this 1 minute data analytics capability. And then finally from there, for the off-shift analysis, we will send either to a petascale offline computing system or to exascale capabilities at either NERSC or the leadership class computing facilities where we'll analyze the data in this off-shift or for the following 4 months. And the division between on-site or off-site will be mainly driven by what kind of computing is expected for that particular experiment. Data reduction is essential, as I mentioned, because it mitigates the storage, the networking, and the processing requirement. We calculated that if we didn't do data reduction, we would have to spend roughly $250 million to build the storage and the processing that is needed to keep up with SLS2.
Ask you a question. About your fast feedback, is that a person looking at the data as it's coming in and then tweaking the algorithms, or is this feedback into the algorithm itself that automatically modifies which data is being saved or what analysis is being done on it?
So,
in the
automatic operation of the data will only happen at this level in the data reduction pipeline, right? The users will be able to see what's going on, and they will be able to tweak the parameters to change how the data reduction works. But this has a fundamental, irreversible effect on the data. On the fast feedback, no. At this point, the data that we save here is also the data that we save for the next 4 months, for the next few years. What happens here is that we try to run a subset of a full analysis that we run here, so that within a minute, the users can decide what should be the next step. Should they move to a different sample? Should they change the injector? There are many operations during data taking that are driven by the feedback that this analysis is providing to the users.
So that could be as simple as we weren't on target with our sample, we need to redo it, something
Yes.
like that.
Yes.
Whereas the online monitoring is more what code I put in there to...
No, the online monitoring is telling you, is the system working properly?
Okay.
Like, are there detectors that are missing,
Okay.
right? But it's not really looking inside...
It's not looking at quality per se.
It's not looking at the quality of the data, it's looking at the quality of the data acquisition.
Okay, gotcha.
Here is when we start looking at the data.
Okay.
Could you talk about the detector data movement mechanism. How do you get bits out of those pixels? How many per pixel? And what's the time flow?
Yes.
And what's the memory technology that's waiting, that could be waiting for it?
Yes. Let me get to this. There is a slide that shows how the data reduction pipeline looks like. And then there are various pictures of some of the detectors that we built for SLS1. So a couple of slides, it will come. So the main point that I wanted to do in the architecture is the introduction of the data reduction pipeline and the ability to offload quasi-real-time data analytics to supercomputers. These are the two main features of our architecture. So as I said, this is how the data reduction pipeline looks like. These are the detectors. If you consider, for example, the CSPAD detectors, right? It is one detector, but it's broken down in many different chips. And then each one of them has a fundamentally independent readout, which is what allows us to pull out this 1 terabyte per second. So it's something that scales with the size of the detectors. When we will go to 60 megapixel detector from the 2 megapixel, 2.4 megapixel that we have today for the CSPAD, all we have to do is to scale up the number of readout nodes. The connection between the front-end electronics of the detector and the readout nodes will use this PGP protocol that we developed as SLAC, which is fundamentally, a point-to-point, real-time, firmware-based protocol with some quality of service capabilities built in that allow us to connect with all the custom detectors that we develop for SLS. PGP is not the only protocol. There are things that operate a lower rate or a lower throughput where we use any technology that is needed, TCP/IP or serial or anything that is thrown at us. So the big detectors, this is what we look like, but we support almost anything.
And digitization are there any issues around digitization?
So the digitization, it happens on the detector itself. Everything that goes here is already digitized. Here we may do some reorganization of the data so that it looks like an actual detector. But here we have already, whatever is the 12-bit that are digitized from the detector itself. We may do, things like calibration later on, but all the hard real-time operations happens on the either on the ASICs or the front-end electronics that is connected to it.
Are ADDs per pixel or are they groups
Yes.
per pixel?
Yes. Yes. So going back to the data reduction pipeline, this is fundamentally from the user perspective, this is like a black box connected with a high-speed InfiniBand switch, which connects a bunch of compressor nodes, and then connects to the fast feedback layer, which is going to be flash-based, and a bunch of online monitoring nodes for the quality of data acquisition that I mentioned in the beginning, the 1 second time scale. So we went through, last year we went through a huge exercise where we started from the detector rates for each instrument, the distribution of experiment across the instrument for SLS2, the typical uptimes of this experiment, what we expect the data reduction to be based on the experimental technique, and then we have measured the processing time for each experimental technique. And this has given us a handle on what we expect the computing needs for the data reduction pipeline and for the offline computing to be. This is what we have used for scaling, the data reduction. This is what we have used to ask for computing capabilities. As I said, beside the DRP, one of the key aspects of our system is the ability to offload computing to a supercomputer. So all the exascale kind of experiments will be offloaded to NERSC or the LCLF. And we have been working with NERSC on this photon science speedway idea, where we stream science data files on the fly from the LCLS beamlines to Cori through ESNet. So the next section is about example of algorithms, just to give you an idea of what we try to do in the DRP. There are 4 fundamental different techniques. One is compression, which can either be lossless or lossy. It turns out that lossless, given the typical entropy of our images, is not particularly efficient. We can typically get a factor of 2. With lossy, we are still working on it, but there is a chance that we can get the factor of 10 that we are looking for. Feature extraction, things like finding the peaks out of an image and move on only the peaks, do a region of interest, integrate region of interest information, do angular integration, which is a very powerful technique, binning, or transform the data into a space where the data are sparse, like JPEG style compression. Or we can do a veto. This is what we will do for single particle imaging or nanocrystallography, where because of the very nature of the injector, you will miss some of the samples. And so we'll be able to detect if one event was a hit or not. Or multi-event reduction, MPEG style correlation of the events. Again, this is something that could help, for example, for XPCS, where we do keep correlation across events. In this section, I will talk about 3 examples of this technique. One is what we call the time tool that we will do in FPGA. This is what calculates the delta between the optical laser and the arrival of the X-ray beam. We will talk about what it means to do lossy compression for nanocrystallography from a reconstruction point of view, and what we are trying to do to do angular integration, which ends up requiring beam center determination. And there are roughly 20-25 experimental techniques that we have identified. I will go through 3 of them, otherwise it becomes overwhelming. So as I said, it's possible to detect the delta between the optical lasers that does the excitation of a sample and the arrival of the X-ray. This is done by taking an image of the reflection of the optical laser through a surface, which changes reflectivity when it's illuminated by the X-ray beam. And this allows us to determine a peak in the signal that then give us the delta in a picosecond between the optical laser and the X-ray beam. This is interesting for us because it's something that we want to implement with FPGAs. Every time that one of these data reduction capabilities is relatively stable over time, and it's not depending on too many parameters, we will try to do it in hardware rather than software. And since this is the same tool across all the LCLS instruments, this is a good instance for us to try FPGA analysis. As I mentioned, doing lossy compression is one of the things that we are studying right now. Fundamentally, we want to know if doing this lossy compression will affect the reconstruction, the resolution of the reconstruction. So what we have done, we got a CSPED image, and we added uniform random noise of the order of 10 plus minus 10 ADU. And then we used these simulated images to go through the reconstruction and see if there is any difference. And what we have noticed is that up to about 10 ADU, we are fundamentally getting the same resolution. So the 10 ADU, 20 ADU is roughly the limit that we are looking right now. The problem is that if we add this absolute noise, the compression factor, at least using these algorithms that has been developed at Argonne, is not good enough, right? We need to go up to 500 ADUs to get the factor of 10 that we would like to obtain. So what we are trying now to look is, instead of doing absolute noise, to add relative noise of the order of 1%, 10%, 1%, and 0.1%. In this case, we can get decent, this is a factor of 7, decent reduction compared to, for example, a G-zip reduction of our CSPAD images. This is still a work in progress. Really, we would like this number to be, somewhere above 10, and we need to determine if this relative error bound introduces too much noise in the reconstruction.
Could it be the case that certain experiments could get away with more and others less, depending upon what they're doing, or is this just a generic statement?
The big advantage of compression compared to other data reduction techniques is very general, right? So we kind of...
So it should be good for everybody if you can get away with it.
Yes, it's just a hammer, at least for all the nanocrystallography experiments. Right? Okay. This is what, which represents maybe 20% of the LCLS experiment. So it's an important technique for us. But again, if you look at stuff like feature extraction, you really need to do feature extraction that is dedicated for that particular experiment. With compression, you kind of try to get away with it. Another things that we are working on right now is determining the center of the beam, because this is what allows then to do radial projection, which is very powerful technique for determining if it is a good event, if there is enough information that you want for that event to move forward. And we have tried different applications. The typical scikit beam application uses scanning for edge finding and ransack for fitting, and it's fundamentally not working for all the science cases that we threw at it. So right now we are trying with this half transform, where you move from this XY view of the image to a radial view of the image, and then we apply later on the edge finding and the fitting. And this seems to be much more robust technique. And these are some examples of where our beam center finding operates successfully. Right? This is a typical CSPAD image. You see, these are the readout unit that I was mentioning before. I think we have like 32 of them in a CSPAD detector. When the beam is going through the middle of the detector, it's relatively easy. The beam can be anywhere. It can be on the side of the detector, can be on the corner of the detector. And this code that we are developing right now is able to adapt to all these different applications. So, as I mentioned, besides the data reduction, one of the key aspects of our system is the ability to offload computing to a supercomputer. This is the data reduction that I showed before. Then we go to a thin but fast flash-based storage layer. And then we move the data over ESNet to the border nodes of the Cori supercomputer, where we start the analysis. We do the full reconstruction, and in quasi-real time, we send back the information to the beamlines where the user can visualize the full analysis in quasi-real time. This ExaFEL, data analytics at the exascale, is a project which is part of ECP, the exascale compute project within the OSCAR Office of Science. And the idea here is that we are developing both the algorithms that are needed to do the analysis, at least for nanocrystallography and for single particle imaging, and to scale the capability of the SLS analysis framework from the hundreds of cores that we have today to hundreds of thousands of cores that will be available on an exascale machine. And then finally, the infrastructure, which is the automation of the data transfer, is the automation of the submission of the jobs, running the analysis, and provide the feedback back to the users. So why is it important to move from the terascale that we adopt today for doing the modeling of the Bragg spots to the exascale that we are aiming for by 2022, 2024? First thing that we will do in the petascale range is this IOTA algorithm, which offers a wider parameter search, and we end up with a much higher acceptance rates for diffraction images, which means that we can then do the analysis with a factor of 5 more images than what we can do today. And then eventually, with techniques like the MTIP algorithm that I will describe later, of ray tracing, we will get into the exascale world, and we will be able to increase the accuracy and also do de novo phasing, which means that we will be able to analyze atomic structure with no known analog. So we don't need any a priori information to do the reconstruction. So on one hand, we'll be able to analyze more diffraction patterns, which means being able to keep up with the LCLS2 data rate, but we'll also be able to increase the detail, the resolution, and the scientific payoff of the LCLS2 science. So the next few slides are about some of the full-scale analysis. The first one is nanocrystallography. There are significant advantages of doing nanocrystallography at LCLS. One is this, what we call diffraction before destruction, where the X-ray is so intense but so fast that we are able to take a snapshot, a diffraction pattern, before the X-ray completely destroys the sample. So we are able to completely avoid the radiation damage, and also we can operate in physiological conditions, which is not something that cryo-EM people can say. And again, this key aspect of doing real-time analysis within minutes provides results that feedback to the users to take critical experimental decisions. Another algorithms that we are developing within the ExaFEL project is diffuse scattering, which is the scattering that comes from any departure of a material structure from that of a perfect lattice. This is a picture that we have been developing to show what it means to have a diffuse scattering perturbation to the perfect lattice. This is a perfect crystal of horses, all on the same phase, and this is the diffraction pattern that you can derive from this perfect crystal of horses. These are horses that are moving, right? They are still in the perfect place in the lattice, but they are moving. They are at different phases. And this is what a diffraction pattern will look like. You still have your Bragg, you still have your Bragg peaks, but then you have all this cloud of information in the diffraction image that contains information about all the differences between the horses in the crystal. Or you can have horses that are in phases but that are fundamentally displaced from the perfect crystal. And then you have again this cloud, slightly different cloud, on top of the Bragg spots. This is development that is being done by our collaborators at Los Alamos. And fundamentally, it can provide extra information and compared to the typical nanocrystallography reconstruction. Another algorithm we are working on within ExaFEL is the MTIP for single particle imaging. This is an algorithm that tries to determine at the same time the orientation, the intensity, and the phase of the single particle that was illuminated by the X-ray. The idea is to reconstruct a 3D structure of a silicon particle using the diffraction before distraction that I just described. We collect thousands of diffraction patterns of randomly oriented single particles. As I said, we don't try to orient these particles in any way. And then, even if we cannot measure the orientation of individual particles or the phases of diffraction pattern, MTIP, through these iterative algorithms, can deduce these two unknowns, orientation and phase, given some constraint. This is the first example where this group, which is the camera group, which is a collaboration between different offices within the Office of Science, has done by imposing this symmetry over the samples. They were able to deduce both the orientation and the phase of diffraction patterns. So this is a very powerful technique, but it's very computing intensive. The iterative nature of this process, this is what will bring SLS2 analysis within exascale. Then finally, we are developing a framework for analysis that will be able to satisfy any experimental techniques, any algorithms that is thrown at it. And what we are working on right now, always within exascale, is the ability to scale from the hundreds of cores that we have today to hundreds of thousands of cores. We are doing this by adopting this Legion framework that will allow us not only better ability to overlap I/O and compute, but above all to provide portable performance on new architectures. And this is becoming particularly important for us. It looks like that even if most of the exascale computer will be accelerated architecture, they will be fundamentally different architecture. And our hope is that by adopting Legion, we will be able to port and optimize the SLS analysis framework relatively easily from one architecture to another.
Can I ask a question? Currently, you've been doing some of the stuff on the KNLs at NERSC. Have you also worked with Titan as well?
We are doing Summit this year.
Okay.
That will be the first time where we try to bring the SLS.
So are you going to use Legion on Summit? Okay.
Yes.
Okay.
Yes, that's the idea.
Okay.
That's the idea. This is how our system looks like. We fundamentally try to offload one event to each core. Then we do calibration. We run the science-specific algorithms. And then Legion is what puts together the communication across the cores before we write the results, visualize, and provide logging capabilities. Right now, instead of Legion, this is MPI.
Okay.
But through Legion, we hope to get better portability across architectures.
And the previous code from the camera group can be dropped in there?
Yes, that's exactly the idea, right?
Okay.
We can do this development in parallels, the framework on one side, and then we plug in this box here what is needed. Another key aspect of SLS2 is that we will try to move more towards automation. We will ask the users to do less and less, to focus on the experiment side, and not to have to fight with analysis at all the time. And so one of the things that we have done within ExaFEL at the end of the last year was to automate all these steps, moving the data, starting the analysis, running the algorithms, and then visualize the information back to the users. So the last slides, instead of doing summary slides, I would like to show you a video that we developed. It's a 5 minutes video, so we have time, that shows how we put together all these capabilities, right? The nanocrystallography algorithm development, together with the scalability of analysis framework, together with this resource orchestration between the beamlines and NERSC.
Department of Energy's LINAC Coherent Light Source X-ray laser at SLAC National Accelerator Laboratory is one of the nation's most important tools for studying materials at the atomic and molecular scale.
This is the CXI.
Among its many uses, LCLS's brilliant pulses of X-ray light provide never-before-seen views of the structures of biomolecules. Researchers from around the world come to LCLS to study these biomolecules using a technique called serial femtosecond crystallography. In this technique, diffraction patterns of crystallized protein are measured on a detector. Complex computer algorithms are then able to analyze and reconstruct atomic structures from these measurements. However, LCLS's X-rays are in great demand, and in order to obtain high-resolution structures of a given biomolecule, researchers may need to capture more than 100,000 crystal diffraction patterns. LCLS currently runs the analysis in parallel over about 1,000 cores, but it still takes hours after the data are collected to determine the structure of the protein. The data analytics at the Exascale for Free Electron Lasers project, or ExaFEL in short, will pair LCLS's crystallography data with ESNet's high bandwidth pipeline and the DOE high-end computing facilities to allow researchers to analyze their data in minutes via a web browser interface. As part of its first-year data challenge, the ExaFEL project recently completed a demo where a user initiates the crystallography analysis on a web browser while the data are being collected. Within seconds, the crystallography data to be analyzed are sent from LCLS to the National Energy Research Scientific Computing Center supercomputers over ESNet. ESNet's data pipeline provides high-performance, high-speed service to more than 50 DOE research sites. SLAC is connected to ESNet at 1x100G, with a second 100G edition expected in the coming months.
Which will become 1 terabit for SLS2.
Within a few minutes, the analysis of the first 7 runs are completed. These runs are merged in a 3-dimensional space. The merged data are phased, and the GUI is automatically updated to reveal a first look at the electronic structure of the biomolecule lysozyme, crystallized with ytterbium. The experimenter can then study the structure in near real time and interactively. Researchers connected via a web browser can receive feedback about the progress of the analysis from anywhere in the world within minutes of the experiment starting. With each set of newly analyzed runs, the molecular model improves as more data are merged in. As a proof of concept, this demo tries to replicate a scenario for LCLS2, where data reduction has been done locally, close to the beam lines, and only the useful crystal hits are sent over to NERSC. In the demo, we analyzed 140,000 diffraction patterns, amounting to 600 gigabytes of data, processed by 32,000 computing cores on NERSC's Core P2 supercomputers within minutes. The LCLS2 upgrade will increase the X-ray laser frequency from 120 pulses per second to roughly 1 million pulses per second, increasing the associated data rate several thousand times over. Ushering LCLS into the exascale era and pushing the boundaries of exascale's real-time computational intensity. ExaFEL will be instrumental to the development of data analysis techniques for LCLS2.
Yeah, this is what I wanted to show for you.
All right. Thank you very much. So just a few minutes here to take a couple questions. Josh?
Sort of in general, in the build-buy decision of different software components, how do you generally evaluate commercially available software and then decide, yes, we're going to just use that, either open source or pay for a license, or just build your own?
So let's look at different components, right? One thing is the overall framework, right? This is what PSANA, the one that provided the scalability, right? That is completely open source. It adopts some typical open source Python tools. It's written both in C++ and Python, and it adopts some Python code that is being developed specifically for beamlines, which scikit beam idea, where we try to provide a Python API to a bunch of high-performance C++ cores underneath. Up to now, we never adopted any commercial software. And I have to say, one of our main competitors for PSANA was MATLAB. And the main difference, the thing that really changed everything for PSANA was when we moved from C++ to a Python interface. Only then people start adopting PSANA and drop MATLAB. Regarding the algorithms, this is very specific techniques that are typically developed by universities. There is a problem there. Many of these universities, institutions, they feel in competition with each other. It's a very different environment than high energy physics, for example, where everything is open source. Here, the data is given access only to the experiment and to the users that run that experiment. And the software, except the one that we develop, that we make available to everybody, that's our main job, the software is not always shared. There are, for example, competing nanocrystallography software packages out there. And that is something that hopefully, as we get more and more into software development, we can intervene and make all of this stuff available to everybody. Because right now what happens is some of the groups that have done the development will use this leverage to get into all the groups that do science in LCLS, which is not what we want. We would like for relatively group with PIs that are not exceptionally connected to other groups, to be able to have great ideas, come to LCLS and do science. So that's one of the missions, as I see it, on my job, to collect all the software from the different facilities and then make it available to everybody. Thanks.
Let's see. Oh, Katerina first, and then Nancy.
So, when you talk about data reduction, are you ever discarding information that you might need later?
It's possible. Yeah, it's
so
possible.
How do you know in advance that you don't need it? Do you discuss with the scientists?
Yes.
So is
yes. We are going through a very painful process right now, where we interact with the users to decide what the data reduction software will look like. Let me say, though, that there are plenty of mitigations in the system. For example, we'll be able to pre-scale the data that comes out of the data reduction pipeline. So some of the events will go through no matter what. So offline, then you can verify but we are not discarding any useful information. The other mitigation is that we will parameterize the data reduction so that it's relatively easy for the users to change what goes in and what goes out, what comes out of it. But it is a big deal. For SLS1, we saved all the data. So now to convince the users that we are able to do feature extraction and not throw away any science is a challenge. But it's something that we need to go through. Right?
But at least you have the data in hand to prove, you could prove to them that what you're doing
yes.
is
Yes.
right.
Yeah,
You know?
we will save a subset of the data, no matter what. Also, an experiment is a few days, so we will have time to correct and avoid throwing away actual science.
Months.
But this is something that in energy physics happens all the time.
Yeah, exactly. No, that's
Right?
that's why I'm wondering.
There is a fundamental difference between energy physics and what we do. In energy physics, typically you have a cross-section that determines the rate of useful events. In many of these events, of these experiments, all the events are useful.
Yeah, but that's also what the LHC experiments are turning to. Because so far we've not really found anything that stands out with a small cross-section, so you really need to look in the bulk now. You really need to make the most of luminosity, so we have similar challenges, I think.
So I was curious, I mean, I think it's really cool how this data converts to this detailed structure that you were showing of the proteins. I was just curious, I mean, what this detail is. I mean, if you give us a little bit more of a taste of what science you're getting out of the details in the structure.
So the typical resolution is Armstrong scale. We can get down to 1 to Armstrong on these reconstructions.
And what does that enable? I mean, on a very big picture.
Much better. Again, this is not my area of expertise, but fundamentally, it allows you to understand how, once you have a 3D electron density of a sample, it helps you understand how it interacts with the rest of the world, right? So you can have an idea of what the weak points of a virus could be.
If I could offer one other science example that's illustrative is something like photosystem 2 is a very large macromolecular complex, has been observed in its photocatalytic processes with this technique. So if you want to observe photosynthesis, that's one of the sites here.
Sort of down at the information architecture level, when you're, for large systems like this, computationally and data storage-wise, what sort of data integrity analysis do you do? I mean, when 10 to the minus 12th bit error rate, when you have a big numerator and you get a hit in your metadata, or you have to worry about a hit in the metadata, do you just buy data integrity from the infrastructure provider, or do you do your own analysis, perhaps making a distinction between observational data, which is more robust, and other data, metadata that's more sensitive?
I mean, from the moment that we read out from the front-end electronics, all the data goes through checksum at all the stages.
Okay.
Is that what you were asking, or?
Yeah. Well, there's the data integrity device. There's error detection, error correction, the cost of that at multiple stages. I'm sort of thinking of planetary probes, where this issue has to be corruption of various portions of the communication.
Look, in the end, for the kind of experiments that we do, if a bunch of pixels,
sure, no problem.
it's not going to affect us, right? After the data has been written the first time, from that point on, we can guarantee that there is no error being applied to it. But it is true that we could have at the ASIC level, we could have modification of the error content of the content of this pixel information. But fundamentally, that is not going to affect the science. that we do later on. Even if we have a few pixels over these 16 megapixel detectors, where the information is not correct, is not going to fundamentally affect the reconstruction. If you notice, the CS pad has all this empty information across the ASICs. Do you notice? And we can fundamentally take that into account and not affect the reconstruction capabilities of the data. So fundamentally, we are resilient to flipping of information, even very early on.
Any other questions? Well, let's thank Amedeo again. And